Hello, everyone. Welcome to our series of webcasts. This year, we decided to focus on Informix best practices, both for new DBAs and for old DBAs. Everybody gets a chance to learn something new. And this month, I'm really excited to have Art Kagel do our talk on disk and data space layout. Art did one 2 years ago. That was one of the more popular talks we've done, and this should be an update of that. So, Art, why don't you take it away? I'll put myself on mute, and everybody should be on mute. If you have questions, save them for the end, and you should see a chat button at the top of your screen. The best way to ask questions is to do a chat to everyone so that both Art and I see it. And at the end of the webcast, we'll go through your questions. So Art, take it away.
All right, great. Lester, if you see something come up in the chat window that you think we should interrupt for, please don't hesitate to jump in and we'll answer the question then. Otherwise, we'll take all the other questions at the end.
I'll do that.
All right. So as Lester said, this is our hold on, there we go. Couldn't get the slides changed. So the webcast series is being done by Advanced Data Tools and myself. Lester is going to do another session next month. We'll talk about what the specifics of the sessions are towards the end. And I'm doing this session this month, obviously. Mike Walker is going to do another session, and I think Tom also has one scheduled coming up. So we're going to talk about disks and storage and DBSPACES, and I'm going to go from the bottom to the top, okay, from the very lowest level to the highest, and I've reserved some time at the end to talk about RAID, just because it's my favorite topic. So here we go. So the first thing you need to do when you're thinking about setting up a new server or making major storage changes to an existing server is to look at the media itself, okay? What are my choices, right? Obviously, you have a choice today between SSD drives, memory chip drives, and magnetic drives, okay? Most commercial systems use 15,000 RPM or 10,000 RPM magnetic drives or the SSD drives. Up until about 4 years ago, the SSD drives were not reliable enough. Their mean time between failure was too short to be considered for most serious database applications. But in the last 4 or 5 years, that's changed, and we've reached the point now where I can say that I recommend to my clients that SSD drives are a viable option, okay? So once we've decided on what drives we want to use, we have to configure them. We can, of course, use just a bunch of disks, use individual drives. Certainly for smaller systems, it's a viable option with large drives available, and we'll talk about large drives also at the end. But one of the things to consider is the RAID level. If you want to get more storage and access to larger files, larger file systems, larger chunks, then you're going to need some kind of an array, right? That could be as simple as a dumb RAID 0 stripe set, could be RAID 1 mirrored pairs, it could be RAID 10, could be RAID 5, 6, RAID Z, whatever. There's a whole bunch of different RAID options. To me, the only options that are really viable, safe, and performant for your database are RAID 1 and RAID 10, period. Nothing else is recommended as a best practice for databases. Okay. Another thing to consider is how, once you're striping multiple drives, whether it's a RAID 5 array or a RAID 10 array or something else, is the stripe size or the block size. How much data sits on each disk before the next block gets written to the next disk, right? How big are those blocks that are written round robin to the various drives that are in the array? Most file systems and most storage administrators recommend block sizes in excess of 1 megabyte, and I've seen them as large as a gigabyte. So Unfortunately, though, for databases, the unit of write is very small, right? Informix writes 1 page or 8 pages. Informix page sizes vary from 8K to 16K. So even with 16K, that's only a 128K write when 8 pages are written, or 16K write when 1 page is written. So to have block sizes that are in the megabytes or hundreds of megabytes doesn't make sense, because we're rewriting the same block on disk over and over and over again, and that can be a bad thing. So I always recommend that you configure the smallest block size that you can talk your server administrators into using. Okay, I like to see 64K, 128K, maybe 256K. Okay, I don't recommend going larger than that in general. Channels, how do the disks, how does the SAN attach to your system, right? You basically have options of dedicated copper, dedicated fiber, or network attached storage, right? NAS and SANs on the network. The things that you want to keep in mind and keep track of is how many channels do I have, because even if you have a 100 gigabit network, right, or faster, then you can, that's a limit on how much data you can send down that pipe. Okay, if you have other things on that network besides that one SAN, if there are multiple SANs and multiple systems besides your single database system, they're all competing for bandwidth. So you may want to have set up your system with multiple channels, whether it's multiple dedicated disk controllers, whether it's multiple network controllers with multiple networks, physical networks out there, so that you can move the amount of data you have to move. And that's one of the studies you need to do before you set up your system. How much data am I going to have to move, and what kind of channels, right, and what kind of storage am I going to have to set up in order to handle that amount of I/O. Okay. Physically, we want to make sure that the array you set up is dedicated only to the database, that there's nothing else stored there. Different applications like file systems, email servers especially, and databases all have very different access patterns. And putting a database on the same SAN as an email server, right, an Exchange server or something like that, is a bad idea, because those I/O patterns are so different. Okay, even a general file system for general file use, the access pattern is very different from a database, and they will interfere with each other. So you want to make sure that your database is stored on structures, physical sets of drives. I'm not talking about separate LUNs that might sit on the same structure. We're talking about separate physical structures of drives from everything else that's on the system, okay? And possibly even from other databases, right? You may have 2 databases that have high access patterns at the same time of the day. You may need to keep them on separate structures as well. I recommend to my clients that you avoid hierarchical storage solutions. That's where the storage system, the SAN, for example, is free to move your data from slower disk to faster disk, or vice versa, from faster disk to slower disk, based on how active the data is. It's usually a bad idea for databases, because what data is active at 3 o'clock in the morning is different data than is active at noon. So you have data that's going to be moved and copied constantly, and that's probably a bad thing. And certainly those first few accesses to that data that's been moved to slow storage, when your workload changes at 7 a.m. or 9 a.m. or 3 in the afternoon, those first few accesses are going to be very slow, and sometimes those are the reports that really matter. Okay. Also, I tend to recommend that you avoid virtualized storage systems for all of the reasons that I just covered, right? You don't know what's on there. Could be other applications, could be other databases, could be news servers, web servers, file system servers, email structures, right? Parts of that could be hierarchical storage, and parts could be slow disk, and parts of it going to be fast disk, and you have no control of where your data is. You may end up with your logical and physical logs sitting on the same array, because that's where there was space when the virtual array system decided to allocate the space. So I recommend you avoid these new virtualized storage solutions. Right? So once we've got that done, now we have to allocate chunks. Okay, so when we're going to allocate chunks, we have to make the decision: are we going to use raw chunks or cooked? In the old days, the decision was easy. Raw was 20–25% faster than cooked. So we avoided cooked files like the plague, except when we couldn't get away from it. Today, with direct I/O, which we'll talk about in a minute, the difference in performance is not that great. So we're talking about what is the real difference between them? Why would you prefer one to the other? So I've got a small list for each of the problems that I have with both, and the advantages of raw. And one is that raw disk is less obvious to people who don't know what your system is built like. Right? The system administrator has no idea what your database is doing. A new system administrator may not even know that this set of LUNs was assigned to the database 6 years ago, right? Long before he came on board or she came on board, and may decide that, or that a file in a file system, right? If you're using cooked chunks, Informix only opens the file and touches the access time for the file when you start up the database. So you may have an administrator who sees the disk is running tight, there's not a lot of free space. Oh, look at that, here's a 30 terabyte file that hasn't been accessed in 6 months because your server hasn't crashed in 6 months and you haven't brought it down. I'll delete the file. And you're not even going to know it, and because of the way Unix works, the database will continue to work, but the next time you boot the system, that chunk is gone and unrecoverable. You're going to have to do a restore at best. So that's my biggest problem with file system chunks. Okay, another advantage to raw is when that raw device is mounted. Okay, and somebody tries to build a file system over it, they're going to get an error and it's going to fail, and your database will be safe. Right. On the other hand, somebody could delete a cooked file. Okay. There's also less chance of interference from other applications, because except for databases, almost nothing deals with raw disk. Okay, so once you're above the SAN level, you ensure that your SAN layout is clean. You don't have to worry that somebody's going to put a file on the file system that holds your database chunks that has nothing to do with the database, just because that's where all the free space was, just you allocated it for future use. Okay. Cooked files, though, have the advantage of being extendable. If you put a chunk on a cooked file, you can tell the database that it is extendable. And when the chunk reaches 80% full, 90% full, 95% full, whatever you define, Informix can optionally extend the chunk and make it wider, make it bigger. Okay. Also, file systems are expandable. So if you use up that space that you've allocated to the file system to hold your chunks, you can allocate more raw disk under the hood, and the system administrators can expand the file system into the new disk, the new LUN, the new disk space, and you can continue to extend your chunks into the new space. So that is an advantage that you don't have on raw, right? You have to always create new chunks when you need to expand things. Okay. And now with direct I/O, as I mentioned earlier, the performance is only about 3 to 5%, depending on the system. Okay. I always recommend to my clients and anybody that asks to avoid using journaled file systems for databases. The main reason for that is Informix's logical and physical logs are essentially a really sophisticated journaling system. Journaled file systems were developed so that when Unix crashes, or your Linux system crashes, at boot time, you can bring the system online faster because the file systems don't have to be checked, because there is redundant metadata and the journals act as logical logs to recover damage to the file system that happened during the crash. But we don't need that facility for Informix. You don't have to check the file system because we have our logs and the logical and physical logs to recover the database after a crash. So it's not necessary and it's kind of redundant. Okay. Also, there are some problems with many of the journal file systems. And I give a longer presentation that covers that extensively. So I'm not going to talk about that now. But the worst file systems for journaling and for performance and for other reasons are ext4, ext5 with the journaling enabled, ZFS file systems because it does copy on write, and BTFS because it's just flaky. Okay, and those are just the popular ones around. Of all the journal file systems, the lightest weight and the least offensive for database files is JFS, okay, the AIX file system, which is also available as an open file system on Linux. It only journals metadata. It doesn't journal the actual data in the file system, so it's not so bad. On Linux, I always recommend that you either use ext2, or if you want the ability to expand the file system without having to unmount it, you can use ext3, but turn off the journaling, which is an option when the file system is mounted. Disable journaling when you mount an ext file system that's going to be used for Informix chunks. And that will let you expand the file system online, but you won't have the overhead and the problems with ext3 journaling. Okay. Some of the SAN vendors, like EMC and others, offer what they call lightweight file systems. Almost all of those lightweight SAN file systems are lightweight because they're optimized to make opening and closing small files very fast. But Informix doesn't open and close a lot of files. It opens all of its files pretty much at the beginning when you start it up and leaves them open forever. So there's no gain from using these lightweight file systems, and they're proprietary. So they may cause you problems down the road. There's no reason to use them. There's no gain from them. Okay. This is a warning. If you're going to set up a VM, right, so Linux or Windows under VMware running your Informix engine, be aware that the performance of I/O on the VM is never as good as it is on bare iron. Okay, it has gotten better over the last 6 years since I figured this out. You know, it used to be awful. Now it's just bad. But it does get better all the time. The VM vendors are working to improve things because of this whole cloud effort that's out there. Okay, and they want to get a big piece of that dollar set. But keep in mind, you need to make sure that the VM is going to give you the I/O bandwidth that you need. You've got to test it, okay, for your environment. Storage pools. You can define a storage pool with predefined list of files from which Informix will allocate new chunks when a DB space fills up, and its chunks are not expendable, rather. And then the DB space can be marked expandable and linked to the storage pool, and Informix will automatically expand the file system by adding a new chunk from the storage pool. Okay, that's really nice. You know, John Miller is fond of saying you can be adding space to your DB spaces while you're watching the football game in your living room with a beer in one hand and a bag of chips in the other. And that's true. The disadvantage is you can only have one storage pool. So all of your DB spaces are going to get space from the same storage pool. Okay, and as I'll talk about in a minute, you need to be able to isolate high transaction rate tables from historical tables, your logical and physical logs from each other, your logical and physical logs from the temp DB spaces from your data DB spaces. You may even want to isolate your index DB spaces from your data DB spaces on different structures, and you can't do that with a single storage pool. You could code your own storage pool management and replace the functions that are built into Informix, but that's a development effort. Okay. The current system only allows one storage pool. DB spaces. When you create a new DB space, there are 3 basic things you need to consider that people sometimes forget. Page size. You want to make sure that you're putting in a page size that is useful for the data that's going to go on there, all right, for the objects that are going to live there. And we'll talk about that in a minute. You need to size the partition table extents. So when a DB space is created, space is allocated at the beginning of the DB space for a certain number of what are called table space, or partition header pages. That's your actual table, All right, those are the header pages that define where your table lives, where its extents are, where its indexes are, et cetera, et cetera. A lot of overhead information about the table. That's where the number of rows and the number of pages is kept on that one page initially. So that small section at the beginning of the DB space has to be sized appropriately so that all of the tables you expect to put into that DB space, all of the indexes you expect to put in that space, all the fragments or partitions you expect to live in that space, have enough space in that initial extent, right? That initial partition table, or in one or two additional extents. Okay, I've seen DB spaces with hundreds of extents because when the DB space was created, either it was before we had the ability to change the extent sizing, or nobody approached it, and we've got the default of 16 pages for the initial extent sizer. Sorry, 200 initial pages for the initial extent and a 100-page next extent sizing. That's the default. Okay, and you can set the extent sizing at the time you create the DB space for every DB space. The only exception to that is the root DB space is created at init time. You have to set that in your on-config file before you initialize the engine. Okay. And the other thing you want to decide is, should the DB space be expandable, right? And do I have to define a storage pool for it? Okay. There are several different kinds of DB spaces. There are normal DB spaces that you use for the root DB space for most of your data spaces, for indexes, et cetera. There are temp DB spaces which are not logged. That's the main difference between temp DB spaces and other DB spaces. They're not logged, they're not checked, they're not rolled forward. The only thing that happens when the server starts up is it looks to see if there are any tables living in the DB space that were left over from a crash, and it drops them. Other than that, the temporary DB spaces, the engine doesn't care much about at startup. Okay. There are blob spaces for dumb blobs. We have unlogged smart blob spaces, logged smart blob spaces, right? You've got logical log DB space, which is new in 12.10. A place where you can put your physical log. If you create a physical log DB space, and that will automatically place or move your physical log into the new plog DB space, the DB space and the physical log will become automatically auto-expanding. So if you suddenly have a large batch job run that needs more physical log space, the physical log will expand to fill the DB space, and the chunk that the DB space lives in will extend itself. It's automatically extendable, okay? Assuming you've put it in a file system that will allow it to extend and then isn't on raw. And there are what's called external DB spaces, which are just basically flat files that you can use when you create your own user-defined types to store the data for your UDTs. The engine doesn't do much with them except read what's in there. Okay, and when you create those UDTs, pointers to that external space data get saved in the base table. When you're building chunks for your DB spaces, should the chunk be extendable? We already talked about this a little bit, right? How active will the data that's going to be there? Is it going to be versus other chunks? So do I need to put this chunk on my fastest disk, on my slowest disk? Right? Should I put it on magnetic media? Should I put it on SSD drives? Another thing you want to think about is where should it be placed in storage? And should you mirror it? Informix mirroring isn't used a lot anymore, but one time that you would absolutely want to use it is if you're creating a DB space or adding a chunk to your root DB space, your physical log DB space, and your logical log DB space, and the underlying structures are RAID 5, and you couldn't get them to set them up as RAID 10 or RAID 1 for you. I would strongly recommend that you mirror them in Informix, because those RAID 5s will fail someday. Not may, will fail someday, and you don't want them to take your server down. Okay. I mentioned this briefly. Root DB space, logical logs, and physical logs should reside in DB spaces that are separate from each other and separate from your data and your indexes. Those three DB spaces are always in the base page size for your server, which is 4K on AIX, Windows, and Mac, and 2K everywhere else. Okay. And you should always make sure to pull your logical and physical logs out of the root DB space. When you initialize a new server, the logical logs and physical logs get created in the root DB space. And the first thing you want to do is create logical log DB space and a physical log DB space, whether it's a plog DB space or a regular one, and move your logical and physical logs out of the root DB space. Okay, because there's a lot of I/O that happens on those three specific DB spaces. Okay, and you don't want them stepping on each other. IBM recommends, based on their own testing, that indexes live and perform best on wide pages. The wider the better. Maximum page size is 16K. So all of your indexes, except for trivially small ones on trivially small tables, should reside on 16K pages for best performance. Your data will reside where it makes sense to put your data. We'll talk about that a little bit in a bit. Always try to access. One of the things you gain from putting your indexes on 16K pages is it's one way of isolating your index I/O from your data I/O. It also isolates the cache, right? Your index and your data are now no longer fighting for access to the cache. You don't have index pages pushing out data pages out of the cache that are then going to be needed a few minutes later and may push other data or index pages out of the cache again. So by keeping the data and the indexes on different page sizes, you get more separate caches and there's less contention for the cache. And your performance will improve just from that. Forget the reduced I/O load by putting the indexes on wider pages. Okay. You want to try and minimize the wasted space. For example, if you have an 1100 byte record and you're using 2K pages for your DB space, then you're only going to get one record, one row on a page. When you go to add another row, it's going to go on a page by itself, and you're basically wasting over 900 bytes for every row in your table, or about 48% of your storage is being wasted. Okay, so you want to make sure that your tables reside on a page size that minimizes waste. Okay. Also, be careful. Another issue is if the row is wider than the page size in the DB space. If you have a 3K row in a 4K DB space, 3 rows, okay, 3 rows are going to sit on 4 pages, okay, because with those tail ends, or maybe even on 5 or 6 pages, because those tail ends that are beyond 2K will go on a remainder page, and yes, the remainder page can hold multiple tail ends as long as they're not too big, right? Then you get into waste again. But that means that every one of those rows has to be accessed by 2 I/Os, and we don't know where the second half is until we read the data from the first page, because that has the pointer to where the tail end, where the remainder is, or where the next part of the record is if it's bigger than 2 pages. Okay, so you want to be very careful about wide rows. Another thing to be very careful of are tables that have large varchar and lvarchar columns, because even though the database thinks those records are longer than a page, even though they may not be, because that 3,000 byte lvarchar may be empty most of the time, and for most rows may have only 200 bytes in it. Okay. By default, Informix won't put a variable length row on a page if the widest version of the row, the maximum size of the row, won't fit. So if you have one row on the page already that's 200 bytes, but the maximum size of the row is 3,000 bytes or even 1,900 bytes, you can't put a second row on that page even though the new row is only 210 bytes, and there's lots of free space for it on there. If you set max fill data pages, that changes it a little bit. Informix will put a variable length row on the page as long as once it's settled, there's 10% of the page left over for the varchars to expand without having to move one of the rows to another page. Okay, but those are things you have to keep in mind when you're deciding what page size to put your variable length column rows on. Okay, I do have two scripts. If anybody wants to send me an email, wants copies of these two, I will send them to you. This is one I call waste. You give it the database name, it goes through, finds all the tables that are currently wasting more than 5% of their storage, and will show you how they would fare on 2 other page sizes. Okay, by default, it doubles the current page size, and so it always shows it on right, by default, I'm sorry, it says on 2K, 8K, and 16K pages. But you can put page sizes on the command line if you want to see what it'll look like on 10K or 12K pages. Okay. And you can see what's important to look at is the waste per row, not the waste per page. Okay, because if we're getting more rows on a page, but we're wasting a little more total space per page, having more rows may mean we're wasting less space per row and therefore less space for the whole table as a whole. Okay. The other one I call new waste all. This one is a little smarter. It does calculations differently for variable length rows, like the first two reports that are showing there, and for fixed length rows. And for variable length rows, it uses the existing average row size. So if you have a very large table or a bunch of large tables, it may take a while to run, but it will figure out the average row size for each table and calculate the waste based on the average row size. So it's kind of an average waste. The waste may be more or less, but it's the only kind of rule of thumb or benchmark you're going to get to figure out where to put the table. And again, the important thing is the last column here, the waste per row. You want to minimize the waste per row. Now, obviously, if this is the only table that's going to end up on 12K pages, and you waste 2 more bytes per row by putting it on 14K pages, which you already have a DB space for, then, put it on a 14K page and live with it. The other thing this one reports, which the other report doesn't have, is the number of rows in the page. Because do we really care if we're wasting 400 bytes per row on a table that only has 4 rows, right? So it's not a big deal. So that will tell you exactly what's going on. So now we've got our DB spaces allocated. We've decided where the tables are going to live. We've decided where the indexes are going to live. Now we have to decide about partitioning, right? Why do we partition? When do we partition? How do we partition, right? How do we fragment the table? So one of the reasons to fragment or partition a table is to get around or past the 16 million page limit, right? Because of the way row IDs are addressed, you can only have a data partition can only have 16,777,215 pages in it. After that, it will start to report an out-of-space error, okay? And it may sometimes report an out-of-space error even if there are in 1 or 2 slots on various pages here and there. The engine does track that, but sometimes it doesn't notice if there are a small number of slots available. So once you're getting close to the 16 million page limit, you may have to either partition the table or move it to a wider page so you have fewer pages in it, right? Move it to a different DB space. So why do we partition? So another reason is to divide and conquer. If we partition the table, if we have multiple partitions, then we can do parallel queries. The engine can scan the multiple partitions in parallel, optionally, and therefore, perform the query in half or a third of the time. The other thing is to allow partition elimination. If part of the filter or the join condition on the table, on the query, tells the engine that it's not going to have to access, not going to ever need to look at rows that live in partitions 1 and 5, then it won't search partitions 1 and 5, and that will again make the query run faster, even if it's not parallelized. But even a parallel query will run a bit faster if it's searching fewer DB spaces, just because of the reduction in IOs, IO weights and things like that. You also can develop your data distributions or update statistics at the partition level, at the fragment level, and that has 2 advantages. One is you'll get more accurate data distributions because the data distributions will be over a subset of the data, and therefore the estimates that are there and the statistics that the engine uses will be more accurate, and therefore you may get better query performance by getting better query plans. And the other thing is, if it comes time to update statistics, if your new records that are being added or updated only live in 1 partition, it is possible to update statistics only on that 1 partition. And that may allow your update statistics jobs that run every night or once a week or once a month to run more quickly, okay? So those are big advantages of partitioning. Another one is to be able to place parts of the table on fast storage and parts of the table on slower, cheaper storage. Right? If you have data that's historical that you're not going to access, unless some regulatory agency comes through the door and asks for it, then it can be moved. You can do an alter fragment and move that partition to slower, cheaper storage, right? And that will free up space on faster storage for new data that is active, okay? So some of the partitioning schemes we'll go to do is pretty quick. Round robin partitioning is simple. It's fastest for inserts. That's its main advantage and the main thing you want to use it for. And it also improves performance when you have many client sessions trying to insert data, okay? You don't get the partition elimination. Adding and dropping fragments may cause the engine to rewrite the whole table, and you can't use round robin for indexes. It doesn't make any sense to the engine, okay? The next original partitioning scheme was by expression. Those expressions are Boolean, and they can be pretty much anything you want them to be, as long as they return a true or false, all right, by some calculation. And they can be, you can have as many partitions as you want with different expressions. The expressions can overlap, so you need to be careful because the data may not end up where you think it's going to end up if your expressions overlap. And you can have 0 or 1 remainder partition, and that will hold all the rows that don't match any of the partition expressions. So let's say you don't have any partition expression that handles nulls in one of the columns. In the expressions, all the records with nulls will be in the remainder partition, if you have one. If you don't, they'll get errors when you try and update or insert them to null, okay? Keep in mind the expressions are evaluated sequentially in the order you define them. So when you add a new partition to an existing by expression table, the evaluation for that partition expression will come last. So if it overlaps an existing partition's expression, for example, the rows that overlap will go into the old partition, not the new one, okay? So you may have to alter, fragment, and change all of the partition expressions so that the new expression is evaluated first, either because there's an overlap or because that's the partition you access most often, and you want finding those records to be fast. So you want it to be the first expression that's evaluated, not the 207th expression that's evaluated, okay? To get around that, more recent version since 11.7, we've had by list, which allows you to give a column expression, and that results in a value, okay, when the expression is calculated. And then you can have partitions for lists of values. So, for example, you can say by list state code, and then partition name values NY, NJ, CT, right, goes into this DB space, all right, and then, you know, California, Washington State go in that partition, et cetera. So you have a list of values, and those expressions are evaluated using kind of a hashing algorithm, and they're much faster to evaluate. And you can have two kinds of remainder partitions, a null specific, explicit null partition, and a remainder partition that functions as way it goes for expressions. Okay. We can have range partitions. You can fragment by range on a date, time, or any numeric column, so integer, short, etc. Okay, and then your partition expressions will say interval of n units. So let's say fragment by range serial number, right? Interval 1 million. And then you can, okay, store it in this list of DB spaces, DB space 1, DB space 2, DB space 3. The engine will round robin put the first million records, first million serial numbers in partition 1, the next million in partition 2, et cetera, et cetera, et cetera. And you can have multiple store in expressions to be more explicit about where you want things to live, okay? You can also have partitions that are similar to a list partition, which have a value. Those are for if you want to define existing partitions in a table or existing records in a table to be saved on the side, and you want new records to be processed by the range partitions. One advantage of range partitions is if the data arrives and there isn't an existing partition for a particular interval of values, like the next million, let's say you have 5 partitions, every million starting at 1 million, when record number 6 million arrives, a new partition will automatically be created by the engine to hold this next section. So that leaves you or relieves you from going into the database every month, for example, to add a new partition for the new month's data. or once a year for the New Year's data. Okay, it can happen automatically. Now, of course, that means the table is constantly growing. So in 12.10, we've got the later versions of 12.10, we have rolling window partition management. You can just define a maximum number of partitions that you want to allow, or you can, in addition to that, you can say, I don't want to allow a partition to get bigger than 30 gigabytes, 100 megabytes, whatever size you want. When those rules are exceeded, then the oldest partition, the oldest interval partition, or perhaps some of those initial partitions can either be detached to separate tables or discarded entirely and dropped, and that's automatic. So not only is the table growing at the end, but it's shrinking on the tail, and that's all automatic for you, and that's really sweet. Okay. Indexes can, instead of partitioning your indexes, which is one thing you can do, another thing you can do to improve performance for indexes is define an index as a forest of trees index. And what we do is we hash on the first one or more columns of the index, and then build a B tree for each hash value on the rest of the key, the part of the key that's after the hash part. Right, so you have index on column 1, 2, 3, and 4, hash on column 1 into 12 buckets. That will create 12 B trees, for each of the value, one for each of the value of the range of values that are hashed together from column 1. And those are B trees that only have column 2 and column 3 in them, but not column 1. So you can't do any, will not be used for range expressions on column 1, but as long as column 1 is an equality expression in the query, you can do range queries on columns 2 and 3 on the rest of the key, on the B tree part of the key. Two big advantages of forest of trees indexes is that, like partitioning, there's tree elimination. The engine won't search trees that don't match the hash value. And second advantage is that because there are fewer keys, right, because we're hashing on the first part of the key, those indexes are all flatter. They have fewer levels, and therefore they are faster to access, require fewer IOs. Okay. And the other thing is, on a very busy system, there's much less contention for the root node of the tree because there are more trees, so fewer users, in theory, will be accessing the same tree. Okay. Now, obviously, that doesn't work really well for maybe serial numbers, but for other things, it definitely does. Okay. Or actually wouldn't work well, let's say, for year of transaction, transaction date, because most users will be accessing the same transaction date and therefore the same subtree. So that's something to consider. Okay. Extents of the tables themselves this time. Prior to 11.7, all the extent information for a table had to live on one page, so you were limited to 300 some odd extents, depending on how many special columns like blobs and L-bar pairs you had in the table, and how many attached, semi-attached indexes were part of the table. The more of those items you had, the fewer extents you had room for on that one page. Since 1170, the partition header page can be extended with additional pages, and that allows up to 32,765 extents. With extent doubling and the 16 million page limit, that pretty much makes the extents unlimited. So it's no longer an issue that you might run out of extents in 11.7 and 12. However, you still have to be concerned that you have too many extents that contain data that's active, okay? Because that will mean head movement if you're on magnetic disk. It will mean other stresses even to SSD drives, although the effect on SSD drives is smaller. Having your data fragmented on an SSD drive means that you will be beating up on the memory cells of the SSD drive, and you will reduce its lifespan, okay, faster, okay? So there is an issue even for SSD drives with having many extents with active data on them. You want to keep that to where each extent holds the active set of data. So in worst case, we're building the new extent and we're still accessing some of the newest data on the last extent. So maybe we're accessing 2 extents, possibly 3, that's good. If we're accessing 30 extents, or we're accessing the entire table, or we're accessing data in the earliest extent and the latest extent, then we have some problems. and we need to defragment the table, or maybe even reorganize it using a cluster on some key so that all the active data moves to one end of the table or the other. Okay, things to consider. So that finishes our discussion of how you build your database. What are the best practices, going all the way from defining your disk drive and selecting your disk drive, all the way up to where do I place my tables and how do I configure the storage for an individual table. So now we get down to my favorite subject, RAID 5 bashing. Okay. For anybody who hasn't heard this before, there may be some new stuff here. If you didn't see my presentation on this a couple of years ago, so I'll go through it fairly quickly. Let's see, how much time do we have left? We got about 15 minutes. I think I can do that. So RAID 5 is more popular than RAID 10. Why? Well, it requires fewer drives to present the same storage capacity than RAID 10 does. And storage salespeople like to present a less expensive proposal when they're requested to present a storage solution for, N terabytes of data, because they know that if they come in with an expensive solution that doesn't have real advantages, somebody else is going to come in with a cheaper solution. So they try to make their solution as cheap as they can. And one of the main ways to do that is to come in with a RAID 5 solution. Okay. The other problem is, of course, that most people don't understand RAID 5 and why it's bad. They trust that the salespeople say, oh, it's perfectly safe. We've been using it for 40 years. And that's true. We have been using it for 40 years. And it's been failing for 40 years. That's another story. So what is wrong with RAID 5? Well, the first and the least important issue to my mind is what's called the RAID 5 write penalty. Okay. RAID 5 write performance is from 30 to 60% slower than RAID 0, than just a plain stripe of the same number of drives that provides the same capacity. Okay, and more so when you compare it to a RAID 10 array. Okay, which can read from both sides of the array at the same time and can write in somewhat parallel. So that is an important issue. The main reason for the RAID 5 penalty is that you have to reread all the other drives when you write to one drive in the array, so that you can calculate parity and write the parity back to a second drive, right? So we call that read, write. Right? We have to read the original data, then we have to reread the old copy of the original data. We have to read all the other drives. We have to calculate parity. We have to write the new data down on disk, and then we have to write the new parity block. So for every write, you're actually doing 2 reads and 2 writes in order just to do a write, versus RAID 0 or RAID 10, where you're just doing 1 write, done. Okay, and obviously in RAID 10, that's a parallel write to 2 drives. Okay, but the most important issue to me is that RAID 5 is not safe. Your data is at risk. Okay, why is it at risk? Well, let's take a look at it. Recovery from a RAID 5 drive takes much longer than recovering from a failed RAID 10 drive, because you have to read all the drives in the array and calculate the missing data, or calculate a new checksum to write into the block on the new drive. Okay, so we have to read, let's say you've got a 10 drive array, right? 9 data drives and 1 parity drive, although we know parity is distributed, but that's the way everybody talks about it. So we got 9 data drives, 1 parity drive. To replace that 1 drive that failed, we have to read 9 drives, calculate parity, or calculate missing data from parity, and write it back to the new drive. Okay. And remember, this is RAID 10. This is RAID 5. The firmware may skip the extra reads. You can already read the data, but it's still going to cost you all of that. And those drives, while they're being read in order to calculate the parity or the missing data on the new drive, are less available to actually do reads and writes for your application. Okay. The performance on a RAID 5 array when a drive is being replaced is about 20% of what it is when it's fully populated. So you get an 80% performance penalty when the new drive is missing, and while it's being repopulated, it's even worse. But just while it's missing, you get an 80% hit, because again, you have to read all the other drives. You calculate parity, right? Calculate data from parity for 8 out of 9 drives, 8 out of 9 blocks, in order to return data from that missing drive while it's missing. And then during rebuild, there's more overhead still. Versus RAID 10, right, which only has 1 over the number of drive pairs overhead. And that overhead only affects reads and writes to the one drive where one drive of the pair is down. All the other drives in the array will be operating at full capacity and full speed. And that's a big difference in performance. But as I said, performance isn't the big problem. So one of the problems with RAID 5, another biggie, is that if you lose a second drive before you finish rebuilding the missing drive, the down drive that you've hot replaced or cold replaced, is that if you lose a second drive, all of your data is gone. It is completely lost. There is no way to recover it except to restore it from backup, assuming the backup is recent. Okay. And for a database, this can mean lost transactions, even if you're backing up your logical logs, because there will be data that's on the logical log on disk and it hasn't been written out to backup yet, right? And that means that that logical log with perhaps 10 minutes or 5 minutes worth of data of transactions is lost. And you're going to be recovering your database, best case, to 3 or 4 or 5 or 10 minutes ago, right? And keep in mind, most drive failures are caused by hardware or firmware problems, and those problems are likely to affect all the other drives that were manufactured at the same time from the same manufacturer, right? And that means that a second drive failure is more likely than not, okay? The more drives you have on the array, 4 versus 6 versus 20 versus 30, the more drives in the array, the more likely you're going to experience catastrophic data loss while a drive is down before it can be rebuilt. And we'll talk about whether that's likely or not. And people say to me, oh, that's not going to happen. Wait. Okay. Whoops, go back. Magnetic drives, okay, suffer from what's called partial media failure. Basically, as they get older, the magnetic fields, the magnetic encoding on the drive begins to go south. On the older drives, it physically flaked off. On the newer drives, they're glass coated. Still, after a while, you can no longer successfully record and write data to particular sectors of the drive as it gets older. That's why you have to replace your drives every 4 or 5 years, whether they're magnetic or SSD. We'll talk about SSDs later too. So when most modern drives, when you format them, set aside a percentage of the sectors of the drive for what are called remap sectors. And that means when the disk itself reads a block of data from the drive, there are checksums. There's a CRC, or a cyclical redundancy code, encoded into the drive for each sector. If it reads that sector and checks the CRC code and it doesn't match, it will use the CRC code to rebuild the data, and it will try and write it back to the same sector to refresh the magnetics. And it will then reread that bad sector to see if the CRC code matched the second time. Okay, if it doesn't, then it will take the sector and move it to a remap sector and mark that sector as damaged and offline. Eventually, since the drive is going south, it will run out of remap sectors. That will be the first time that the drive reports to the operating system or even to the controller that there's a problem. All of this time while your drive is going south, nobody knows about it. The controller doesn't know, the SAN doesn't know, your operating system doesn't know, you certainly don't know. Okay, but your drive is going slowly south. Okay, and that starts somewhere in year 3. So eventually, you're returning data from those CRC codes, and that's when you start to get error codes reported to the operating system, because even the remap sectors are reporting errors, or there's an error from another sector that hasn't been remapped, but there's no place to remap it to anymore. Okay, once you're returning, at some point, you're going to get too many bits that are bad for the checksums and CRC codes to repair them, and that means your drive is going to begin to return garbage. If you don't read that sector, you won't know there's garbage there. So if you have garbage on drive 2 and drive 3 fails in RAID 5, when you rebuild drive 3, now drive 3 has garbage on it too, because it was built with the garbage on drive 2. Okay, so your garbage is now spread to 2 drives, maybe later 3 or 4, on a sector that you haven't read in months. Run the year-end report, and suddenly you get errors or you get garbage. Okay. SSD drives. People say, well, it's not magnetic, doesn't flake, not a problem, it's better. No. SSD drive memory cells have a finite lifetime. They count the lifetime in write refresh cycles. Obviously, there are millions of write refresh cycles before the cell fails. But it is a real problem. And so the way SSD drives work is when you read a sector and write it back, the drive actually randomly selects another sector to write that data to and puts the original sector at the end of the list of sectors to use for the next write. Okay. So your data is constantly moving all over the drive, but that's okay because we don't have head movement problems, right? There's no latency for moving heads on an SSD drive. But again, over time, all of those sectors will eventually get close to their lifespan limit, and they will start to begin to return garbage, the same way a magnetic drive does, with the same results. Okay. Another problem is those sectors, those memory cells are fairly large compared to a database page of 2K to 16K. Those sectors are much bigger than that. Their minimum, as far as I know, the smallest of them is 256K. So you're going to be writing a lot of data set pages to the same memory cell on the SSD drive. And that will cause that data to be moved not once, but many, many, many times during the day, okay, as you write page after page after page. And that just makes the drive go south and hit its limits that much faster. SSD drives used for databases don't last as long as SSD drives used for ordinary file system applications because the write patterns are different, okay? So you must replace those drives again, just like magnetic drives, every 4 to 5 years. They have to be replaced. So how is RAID 10 better? Every drive in a RAID 10 array is mirrored, has a complete copy on another drive. You can read different sectors from both sides of the mirror. That means RAID 10 read performance can be as much as twice the read performance for a RAID 5 array or even a plain RAID 0 stripe, okay, at least for short periods, okay? Now, RAID 5 will sell you, it also can write faster because, again, we don't have to calculate parity, right? The RAID 5 vendors will say, well, we can get around that. We'll give you cache, lots of cache. Cache will solve the RAID 5 write problem, and it will improve your burst mode, peak load, read speed, and it will be just as good as RAID 10. Yes, but you're replacing a $900 drive with $5,000 worth of memory to get the same performance. It makes no sense to me, economically or logically, okay? By the way, everybody in the industry that doesn't have to sell storage arrays agrees that RAID 10 is safer than RAID 5. Everybody I've ever read who's written about it. Okay. Now, when you recover a RAID 10 array, as I mentioned, you only have to copy the data from one drive to one drive. All the other drives are not affected. Okay. And you don't have to read parity, you don't have to calculate parity. You read data, you write data. The whole drive gets written relatively quickly. That reduces the possibility of losing a second drive while the failed drive is being rebuilt, because it doesn't take as long to build it. Another thing is, even if you do lose a second drive, the probability that that drive is the other mirror to the one that failed is considerably lower than some drive on the RAID 5. Some second drive on the RAID 5 fails, and you lose all your data. On RAID 10, you can only lose all your data if both sides of the same mirror fail. Okay. And you can reduce the possibility of that because, remember, I mentioned that most drive failures are caused by hardware and firmware problems that may affect multiple drives in the same manufacturer's lot. Fine, build the two sides of the mirror from different manufacturers' lots. You minimize the probability or even the possibility that that's going to happen to you. Okay. Certainly, it's much lower than it is, much lower than RAID 10, 5. Okay. RAID 10 can survive the loss of half of its drives. One whole side of the mirror, okay? And it could be different size for different pairs, and nothing gets lost. Partial media failure is less of a problem for RAID 10 because you're not propagating data from one drive to another. So yes, you might get one drive going flaky, but its mirror probably has good data on that particular sector, and the array will read the data from the good drive and tell you that there's a problem, and you can replace the damaged drive and rebuild it. Is there a possibility that there's some other sector that's bad on the mirror drive? Yes, but it's much less than the problem with copying data from one drive to 20 others. Okay. SSD drives, because there's no checksums being calculated, right, in RAID 10, One write is one write. One write on RAID 10 is one write on each of the drives on a RAID 10. One write in RAID 5 is two writes on a RAID 5 array to two different drives, because you're writing the data and you're writing the checksum block. So your drives in RAID 10 will last longer, whether they're memory or SSD, but especially for SSD drives. So again, if you're replacing your drives regularly, you're safer with RAID 10, because your SSD drives are going to get replaced longer before they fail, or are likely to fail. Okay. So I said we're going to talk about why these are real problems and why drives fail, right? And well, not why, but anyway, the people up at CERN in Switzerland, where the Large Hadron Collider is, and these are all physicists, all bright people, were losing data because they store trillions and trillions of data points every day on these massive RAID 5 arrays originally. And they wanted to figure out why they were losing data, okay? So they set up some specific tests, and they read and wrote the same blocks of data, files that were several megabyte in size, over and over and over again over the course of months and months. And what they determined was they got drives that failed, and sometimes it took the array down because it was RAID 5. Sometimes it didn't. But what they found was that most of the failures, about 80%, were caused by hardware and firmware failures. Another 10% were caused by having the wrong firmware on the drive. Firmware for hardware version 3 was on a drive that was version 4. So it was the wrong firmware, and that, again, is a manufacturer's lot problem. 90% of drive failures were caused by a manufacturer's problem that could affect an entire lot of drives. But it's not going to affect the next lot because they discovered it and they fixed it, right? Partial media failure, they found, accounted for almost all of the other 10% of the data loss that they were experiencing, and that percentage was the same whether the drives were magnetic or SSD. As the drives aged, they started to lose bits. They also decided there was a small amount of data that they were losing on perfectly good brand new drives, and they attributed that to cosmic ray damage. That cosmic rays were penetrating the drive casing and flipping bits on the drive, and that was causing garbage. Okay, keep in mind, CERN is underground. Your data center is not. So you're a lot more likely to get cosmic ray damage than they were, and they found that it happened. Okay, I'm not commenting on that beyond that. So one of the things that you know, when you talk about the lifespans of the drive and how long they live, the drive manufacturers go, but you're not buying commodity drives from Staples for $69. You're buying our high quality super duper duper drives for $1,000, you know, and they're better drives. Well, it turns out a study that was done, not by me, not even by CERN, but by the storage industry itself, okay, determined that the lifespan and failure rates of premium drives are virtually identical to commodity retail drives that you can buy for $69 from Staples, okay? They fail at the same rate, pretty much. And also, according to the storage industry study, the failure of a second drive in an array is 4 times more likely than the single drive's failure rate. Statistics would say the second drive is just exactly as likely to fail as the first drive was. Turns out, in practice, it's 4 times more likely to fail than the first drive was in the first place. So that means the more drives you have, the higher your probability of losing your RAID 5 array to a second drive failure, because it does happen. It's not rare. Also, the writes to a RAID 5 array are not atomic, and that means they're not guaranteed. If you have a hard power loss, somebody pops the plug, you know, between between your battery backup and your RAID array, right? When half the drives have been written to, your data's toast. Don't laugh, it happened at Bloomberg. Some engineer decided there were 2 power cables that were crossed. He pulled one out of the wall and plugged it back in the other way around. You know, the array was toast, had to restore. Larger drives take longer to rebuild, and that increases the likelihood of losing a second drive. But it's worse than that, because a recent study, also by the storage industry, concluded that drives over 1 terabyte are statistically likely to suffer from unrecoverable multiple bit dropouts. That's because the number of bits on the drive beyond 1 terabyte exceeds the bit failure rate. So statistically, the drive is going to lose so many bits per billion, and there are more bits than that on the drive. So it is statistically likely to lose data. Okay, you absorb that. The error rates. Now, that's just based on the error rates. CERN's study determined that the error rates were not as high as they were advertised. The official rate on the drive was somewhere around 10 to the 16th bits for the drives they were looking at. Their experience showed that they were losing 1 in 10 to the 7th bits, okay, or about every 1 million bits, which is about 125 kilobytes. So if your drive has more than 125,000 kilobytes, you are likely to lose bits. And if some of those bits happen to be on the same word as other bits, you're going to lose data. It's going to be unrecoverable. Okay? And all of that together explains why I say no RAID 5. That's pretty much it, guys. All right, that's me, my contact information. You guys have questions after we end this, and we can go over that. Lester's got the next webcast coming up on April 20th. He's doing a webcast on backup and recovery and on high availability and DR, disaster recovery. Okay, in May, Lester's going to finish his on-config talk from last month, and then Tom and Mike have sessions in June and July. Okay. We've got the IAUG conference is coming up April 23rd to the 27th. It is the best place to learn crap like this, okay? You will get sessions, obviously, from me. I'll be there. I'm doing 2 sessions, both of them brand new. Lester's doing a new session, and Mike Walker's doing a session, I believe. We've got a whole bunch of people from users doing sessions. We've got IBMers doing sessions. It is the best place to go to learn about Informix and also to get access to IBM Informix technicians, to the support people, to the managers. Senior management will be there. And we've got a really cool talk from an IBM engineer. Okay. Here's some links that are useful. Training. ADTT Advanced Data Tools Training. The next class is on April 10th. It's a 4-day class for database administrators. So it's for basic administrators that have to work with Informix for the first time or just need a refresh. There are still 2 seats available for that class.
And Art, if I can jump in, there's only one seat left. There's only one.
That's as of yesterday.
as of during the last half hour, someone registered. Perfect.
All right. Lester and I are also doing the advanced class, performance tuning, in July, and that's always a lot of fun. And one attendee told me it was the best 4 days he'd spent in his entire life.
And if I could add something there too, Art and I are also doing an advanced class for a company in Malaysia in the next, it's about 3 weeks. We're doing it on Singapore time, so we'll be up all night teaching the class. If you want, we do any of our training specifically for a company. If you have 4 people who want to take one of our classes, we'll do one specially for you, a private class just for your company.
All right. So let's get to questions.
And right now, I don't see any.
Okay. All right.
If anybody has any questions, please open the chat window and type away.
Do you want to say anything about this slide while it's up here?
Hang on. There's a question on the email address. Oh, I was going to ask you this, Art. The wasted space script.
Yeah.
Can you send that to me, and I'll put it with the slides so that people can download it directly?
Sure. But my email address is coming up on one of the next slides, so you can catch it from there. But Lester will have it up when this recording goes up.
Yeah, and that question always comes up. Give me a few days, probably by Monday, I'll have the recording of this up for anybody who missed it.
All right. Do you want to address this slide while I've got it up?
Not really much to say. This is what we do. Advanced Data Tools is a little company. We focus strictly on Informix performance tuning. We do 24/7 remote DBA monitoring for about 100 servers. We do training. We do performance tune-ups. And then we do large Informix consulting projects too.
All right. There's Lester's email address and the Advanced Data Tools website, advanceddatatools.com. All right. There is the IIUG conference. If you want to go register for the IIUG conference, you can go to iiug2017.com, .org rather, and you can register there and find out. All the sessions are up now. You can see what sessions there will be, and also on the extra day what the tutorials will be.
I just had a question on training. The training location is here at our office in Annandale, but everybody takes it online. You can take it from your desk as long as you have access to WebEx like you do today, and you can SSH into our training server. Each student gets their own separate training server, and you just need to have PuTTY or a Unix SSH client to access that. And that allows you to get into our training servers.
All right. Thank you, everybody.
Cool. Well, thank you very much, Art. Thank you, everybody, for attending. And I look forward to seeing you at the next one.